First part of this question, number 10, I like this one, is we've got a table there and we've got the number of sixes that we achieved when we rolled a dice 5 times. And we rolled this dice over and over again. So we did it 500 times. We rolled it 5 times, 500 times. And we can find out what our mean and our variance is using our calculator. It tells us that the mean is 1. And also the variance, so the standard deviation here is 0.8944. And if I square that, that will give me my standard deviation is 0.8. Now, we're rolling this dice 5 times each time, aren't we? So the probability of getting this 6 on the dice is not actually 1/6, is it? Because the mean turned out to be 1. So 5 times p equals 1. N times p is the expected value of x. So I'm getting p is equal to 1/5 at the end of that. Based on the mean of the data, estimate the value of p. That's what I've just done. Using the value found in it, find out the expected value of frequencies in 500. So I've now got to find out what we expected them to be with p equals 1/5. So using that distribution menu, I've got to do that loads of different times. I've got to do this for the 0, 1, 2, 3, 4, and 5. But that's when the list one is more useful. So I'm just going to go to the menu, statistics. I'm going to go to distributions, binomial. I want to do a binomial PD. And now the data is already in list 1, isn't it? The data is already in list 1. And I want to put, there it is, in list 1. The number of games is 5. The probability is 0.2. And I want to put the results. Let's put the results in list 2. And now it gives us them. We now need to. So that's just given us the probabilities. We actually want to know what it is as 500 times that, don't we? So I'm going to put 500 times list 2 in the top there to find out how many we expect to have in each one. So that is, should we round them to the nearest one? That's 164. That one's 205. That one's 102. That one's 26. 4 is 3. And I didn't do 5. That's annoying. 5 is 0 again, actually. So that's what the model tells us. This is what we actually got. I'm just copying this down from the book again. This is the values that we actually got, and you can see how ridiculously close they are. Even it would just suggest that they made that data up. It does look very, very similar. Part D, how does the variance of the data support the use of the binomial distribution? So if it is a binomial, the variance, of course, is n times p times 1 minus p. And so 5 times 0.2 times 0.8. And what is 5 times 2 times 5 times 0.2 times 0.8 gives 0.8. And look, 0.8 is exactly what the variance was earlier. So we would expect it to be 0.8. Everything adds up. So you got that. I mean, me using the table to do all of that was just trying to do it in a shortcut, trying to do it all in one go to see all of those things there. Of course, you could have just found out what each one was in the usual distribution menu. Just would have taken longer.